Hi, let me introduce vprobe. Maybe the name is not final, but let's call it vprobe. And the product looks like this. And the purpose of the product is to wirelessly transmit signal from here to here. So you don't need wires to your scope. The vprobe can be used to use when you want higher isolation, or when you want just less cables, or when you want to have the probe farther away from the scope. So let's turn it on. First, the product scans for the most empty frequency and starts transmitting on that frequency. And now the product is transmitting to the receiver. So let's sync the receiver by just turning it on and off. So now the receiver is synced to the probe, and currently on the probe you can see a real-time reading, and the probe is compatible with the most standard oscilloscope hardware pieces like ground wires, ground spring, and I don't know what this is called in English, but that part. And you can use the microprobe to measure voltages, and the voltage is of course transmitted to the oscilloscope. And you can select different modes. You can select X10, X1, and you can select 100 kilosample per second at 12 bit with ECC. So it's more probable that the signal will reach the oscilloscope correctly. Or you can select 200 kilosample per second, 8 bit, and X1 and X10 in both. And you can also select X1 1.8 megasample, 1.6 megasample. And then the threshold voltage is 1 volt. I don't know if that is in focus. Yeah, but this is a simple interface for changing the settings, and the settings gets transmitted automatically to the receiver, so it knows the setting and is able to decode it correctly. So let's set this to some reasonable, so now it's at 200 kilosample and 200 kilosample and 8 bit. And the range is plus 12 to minus 12 volts. And in X1 it's 1.2 to minus 1.2. I will also add a mode where it can instead be from 0 to 24, or from 0 to 2.5 at 2.4. So let's do some simple measurements. So this is just some board I made with 5x5 timers, so we can do some simple measurements. So let's hook the probe up to measure one of the signals. And now on the scope you can see the signal. So let's zoom in. And let's also connect an ordinary scope so you can see that the signal is correct. And let's pause and zoom in. So here you can see that there is some latency, and there is of course some latency because the signal is transmitted wirelessly, and the latency is around 40 microseconds. It depends a little bit on the mode you're in, but the latency is quite repeatable. It's always 40 microseconds in this mode, or it seems to be 50 microseconds. Yeah, but it's very repeatable. So each package has the same latency. Yeah, so you can see that the signal is correct, and if we set up the scope to instead trigger on the signal, let's trigger on the true or the wire signal. You can see that there is some jumping because now we are at 200 kilosample, which means that it's 5 microsecond per sample. So if we zoom in to 5 microsecond, it of course depends on the phase between the true signal and the sampling. So in this mode it will only be accurate to 5 microseconds. And if we go to this, you can see that there is some overshoot on the true signal, and that overshoot also is on the sample signal. But let's say you want to have higher, let's say we want to have better than 5 microseconds. We can just go, and now this measures the DC voltage, so the average voltage. Then we can go to the digital mode. And here you can see that the latency is a little bit shorter. It's quite exactly 40 microseconds. And you can see that the signal is true to around a microsecond. There is some jumping, of course, at about the sampling frequency. But yeah, looks like that. And we can measure an even faster signal. So let's go to a quicker signal. So this has a low time of about 3 microseconds and a high time of about 6 microseconds. And you can see that the signal is coming through. This is of course not meant for high performance measurements. Then a cable is way better. This is meant for when you don't want the cables, and it's also very convenient to be able to see the voltage. Quite often for me, I measure on a board, maybe I see, yeah, I have 5 voltage, I have 3.3 voltage, I have 12 voltage, and then I start looking at the signals. And interpreting the DC value from a scope can be quite hard. I think it takes at least a few seconds to understand where you are. And you can turn it off. And it's charged via USB-C. And it charges. And the battery time is about 8 hours. Maybe that will change, I don't know. And yeah, that's about it. This is how it looks on the inside. It's a OLED screen, a small microcontroller that has a Bluetooth radio, but it's not using Bluetooth, it's just using the radio in a raw package mode, so to say. And the battery and a USB connection and one button. Yeah. And currently the plastic is just 3D prints. I don't know if that will be the way, or if I will do some sort of injection molding tooling. And now there is some build quality issues because it's not done, of course, but it will be better when the product is done. You can also do calibration. So if I connect this short, turn it off, and then when I turn it on, I hold the power button. It's calibrating itself. It's offset calibration. And you can also change between left-handed and right-handed. So now it's left-handed mode. You do that by plugging in the charging and pressing on the button. Then it changes between right-hand and left-hand mode. Well, I guess that's all there. Maybe I can show the receiver as well. So currently the receiver looks like this. It also has the same processor. And let's see if I can make some sort of focus. Yeah. So it has the same processor, and it's, well, this revision of the board has 2 USB connections, but I think the final will only have 1. So if you have 4 receivers, then you will need to have a USB-A to 4 USB-C cable. But that's, I think, way neater than having a bunch of USB-C to USB-C jumper wires. Yeah, so that's how it looks. It will also be, of course, some sort of plastic case for it. And this is the transmitter. Very simple and quite cheap.